Hey guys, so for your notes today, please call them 10.1c, experimental versus theoretical probability. And to start with, in class today for the warm-up, I had you guys define what probability was for you. Mathematically, the probability, so P for probability, of an event occurring, so probability of something happening, is the number of favorable outcomes over the number of possible outcomes. Okay. So mathematically, we use this ratio definition instead of saying like the chance that something's happening or the likelihood that something's happening. We define it specifically as the fraction or the ratio of the number of favorable outcomes over the number of possible outcomes. And then this begs the question, the difference between experimental and theoretical probabilities. So today in class we were playing that game, the Crossing the River game, and you guys were rolling the numbers and moving them across the river, and some of you were really smart and you said, oh, well, I know that 7 gets rolled with a really high likelihood. And so you were putting all of your tokens on 7, and maybe just a couple on 6 and a couple on 8, right? Just in case you rolled some 6s or some 8s. And you moved them across, but probably what you found is every once in a while you roll a 4, and every once in a while you roll a 10. And if you start with all of your tokens on your 7s and 8s like they are right now, where they're all centered, you're getting a lot of turns where you don't get anything crossing the river because you're losing out when you roll a 4, nothing crosses. Alternately, some of you guys were like, oh, well, I want to spread out my chances of hitting one of these bad boys, and so I'm going to put 1 token on every number. And so you spread your tokens out, so you're putting 1 everywhere. Now, hopefully you realize that if you put a token on 1, you're never, ever, ever going to win the game because there's no way to roll a 1. That's impossible. And so I bet some of you put a token on 1 kind of not thinking about it at the beginning, and then after you played the first game realized that was kind of a silly mistake to make, and then quickly moved that token off of 1. Well, so in class, what I did was I had you guys come up and tell me your overall experimental probabilities. So if you look at this graph right here for the experimental graph, by the way, I'm going to have you sketch this graph on your notes. So if you need to, go ahead and pause it right now and sketch real quick this bar graph. Make it look close to what you see on here. And then you can just unpause it and keep playing after you get it drawn on. Okay. So if you're just coming back from this being paused, we're looking at the experimental probability. Now notice on the side here that our numbers are going all the way up to like 140. What this means is if I look at 7s, it means in class the other day we rolled a little over 140 7s. And that makes sense because a 7 is the most likely thing to be rolled. And then it looks like for 6s, we rolled about 126s. We rolled just over 85s, etc., right? Now, if you look at experimental probability versus theoretical, experimental probability is when we're actually doing an experiment, right? That's the base of this word. So this is the number of favorable outcomes. I'm going to put number of favorable over the number of total. But in this case, the number of total outcomes is dependent on how many times we roll the dice. If as a class we roll the dice 500 times, our total number is going to be 500. If we roll the dice 1,000 times, this is going to be 1,000. And so experimental probability is constantly changing versus theoretical probability. So you might have to pause here because I would like for you to copy the theoretical probability down in your paper also to copy this bar graph down. So go ahead and pause it and copy this guy for me. And then when you come back, notice here the theoretical probability of rolling a 7 is 6. That's never going to change. There are always 6 ways to roll a 7, and we saw that the other day when we made our dice table. And then there are always going to be 5 ways to roll a 6 and 4 ways to roll a 5. These are the number of ways doing it if we're just listing out the possibilities, not thinking about rolling more than once, but just the number of possibilities on any given roll. So for your notes, underneath those 2 bar graphs that you just added, right? I guess I'll leave them here to remind you that they should be on your notes. So the experimental probability is constantly changing and is based on the experiment. And when I say experiment, I'm using that word loosely. Like, for instance, taking a set of die and rolling the die and getting a 7, that's an experiment. I just rolled 1 7 out of 1 roll. So right now my experimental probability would be 100%. The only things I've rolled is 7s, right? And then I roll again, now I rolled a different number. So now I rolled 1 7 out of my 2 rolls, and I've rolled a 9 out of my 2 rolls. So a 7 and a 9. So now the probability, the experimental probability of rolling a 7 is 50%. The probability of rolling a 9 is 50% also. Okay, so these probabilities change constantly as the experiment goes on. Whereas theoretical probability is constant. It's unchanging. It does not change. It's based on counting the number of possible outcomes. Right? So theoretical probability is based on what's possible, on what might happen. Experimental probability is based on what did happen. So based on experiment, I'm going to put in parentheses here what did happen, what actually happened. Whereas theoretical probability is based on what might happen. So one of them is looking forward, and one of them is looking backwards in the past. In experimental probability, you're looking back in the past saying what happened. Theoretical probability, you're looking forward to the future and you're saying what might happen. Now, notice that when your numbers get big enough, when you get enough rolls, these two probabilities start looking an awful lot alike. And in fact, if we were to keep going with the experimental probability and do this, roll a set of dice like 1,000,000 times, it would get even closer to this theoretical probability. The other thing I want you guys to notice is that these bad boys look awfully like our bell curves that we were talking about in our stats chapter. Remember, you guys would be asked to find the probability that, like, I don't know, a man was under 70 inches or something like that, right? And you were drawing your bell curve. Well, the bell curves that we are using are coming from this underlying probability and the idea that, like, if you have enough trials, enough rolls of the dice, that you're getting really close to the actual probability. Okay. So the last thing I want you to add on your notes is that experimental probability gets closer and closer to the actual theoretical probability as the number of trials gets larger. And when I say number of trials, I mean things like the number of times you roll the dice. So rolling the dice once, that's 1 trial. Rolling the dice twice, that's 2 trials, 3 trials, right? The more trials you have, the closer the probabilities are going to get to each other. Now, last but not least, I told you that if you took the notes over the weekend and paid attention all the way to the end of the video, that I would give you a hint on how to win crossing the river. Okay? The way to win crossing the river, it is a game of chance, so, you never know. Somebody could roll a 7 12 times in a row and beat you. You never know, but that's probably unlikely to happen. What's most likely is you're going to mostly hit 7s and 6s and 8s. So you kind of want to make this almost like a bell curve too, where you put most of your chips in 6s and 8s and 7s, right? And maybe some 5s and 4s. But then, because you want to spread it out so that you're not losing out when you roll like a 2 or a 3, right? You might probably have like 1 in the 10 spot, maybe 1 in your 4 spot. Let's see. Maybe I'll bump this guy over to a 3, right? You want this to kind of look like a bell curve. And if you do that, if you set up your Crossing the River game board so it looks like a bell curve, you're going to have a much higher likelihood of winning the game versus somebody who spreads it out or puts like 2 unevens, whatever, and is just sort of randomly making a pattern. You're going to have a way better chance of winning. All right, we will be playing this game again on Monday and doing a little more probability with it, so good luck.